Welcome to Lab 4, Oscillations. The purpose of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring, and use that model to predict the future motion. The result that we got was that the predicted motion was similar to the experimental motion. However, it's hard to precisely predict because of small forces that could be acting upon the object. The main principles that were used in this lab were Newton's second law and the energy principle. We used Newton's second law to make a model of the motion and used that to find the spring force. We could then use the spring force to predict the motion of the mass. We put the energy principle to a test by seeing if the energy principle would apply to this predicted motion that we have created. We tracked the motion of the mass on the spring by putting the video into Tracker. We used the tracker to watch the motion of the object as it oscillated on the spring. Through this, we could see over here the different periods that it would take for the oscillations. We found the average period by taking positions at three separate periods apart and dividing them. This can be shown here on the formula page. We know that the period is equal to 2 pi times the square root of the mass divided by k. We are trying to find k, so if we can solve for everything else, we can rearrange the formula. We know that 3 periods takes 4.463 seconds, so that an average period would take 1.49 seconds. Once we have this information, we can rearrange the equation for k, such that k equals 4 pi squared times mass divided by the period. We got that k equals 7.15. We then wanted to solve for the length of the spring. We were given that the relaxed length is 0.7 meters. We are also given that the mass of the object is 0.402 kilograms. Using Newton's second law, we know that the force of gravity is equal to the spring constant. We can rearrange this formula and solve for the stretch length of the spring, which is 0.149. Once we have all of this information, we can then go to Python and create a code for this. We insert the mass of the ball, the initial position, which is found through Tracker, and the initial velocity, which is 0. We then go through, choose a time step, and insert all of the constants that we are given. We know that the gravitational is 9.8. We insert the spring force and L naught, which we just found from the formulas, and also inserted all of the other formulas needed to compute the future motion. We used the potential energy, which is k equals 1/2 times the ball's mass times the magnitude of the velocity squared. We also used the two different potential energies, the potential energy of the gravitational force and of the spring force. We are now putting the energy principle to a test by seeing if delta E is equal to the kinetic energy plus the two different potential energies. We insert all of the formulas here so that we have F gravity, F spring, F net, and everything else that we will need to find the delta E. When we run this code, we will see two different objects moving around the spring. One is the object of the predicted motion from the Python model, and one is the experimented motion from the CSV file here. When we run the code, we can see that the blue ball is a predicted motion, and that the red ball is the experimental motion. Once the model is finished running, we can see that the red and the blue balls both end up in the same place. Throughout the model, they are slightly different. This could be because of user error when tracking the data in Tracker. Over here, we can see the oscillations of all of the energies that we tracked. The blue line represents the change in kinetic energy. The red line represents the change in potential spring energy, and the green line represents the change in potential gravitational energy. While these are oscillating, we can see that the yellow line in the middle represents the total change in energy. This is correct because we know that the delta energy equals 0. In one of the what does it mean questions, it asks if this fulfills the energy principle, and it does. There is no work being done on the system from the surroundings, and this is shown seeing as the delta energy equals to 0. All of these forces add up to be 0. We can also change our Python code so that it shows the experimental versus the predicted data. The predicted data is shown in blue, and the experimental is shown here in red. They are very similar throughout the whole oscillation, however they do vary slightly. Again, this could be because of user error when plotting the data on Tracker. The second what does it mean question asks about the difference between the oscillations in the x and y directions. Here, we are showing the oscillations in the y direction. If we change this, we can see the oscillations in the x direction. The difference is that the oscillations in the y direction have an average period of 1.49 seconds. However, the oscillations in the x direction have an average period of 1.646 seconds. This could be because of the different gravitational pulls on the object. Looking at it in the y direction shows the spring mass system, whereas looking at it in the x direction shows more of a pendulum motion. Everything we have discussed relates back to Newton's second law and the energy principle, and the models that we made prove that both of these work for the spring mass system.